we know that if two stars in a binary, they can be binary for thousands of years. However, when they come very close to each other, they come up losing energy and angular momentum. As they come close to each other, they speeds up, and during their speed ups, their amplitude, the gravitational wave that they release, they are always releasing gravitational wave, but the amplitude of the gravitational wave when they are very close to each other is quite high, and then they can be probed using our LIGO detectors, which were done for the case of gravitational wave 170817, where two neutron stars merged, gave rise to a this part is theorized, and hypermassive neutron star, which ultimately collapsed to a black hole, and we got the signal for this inspiral part. We didn't got any signal from the post merger signal, but we got signal from the inspiral part, and which was recorded. And then all the physics that we are talking about, neutron star binary mergers, and started. Okay, this multi-messenger astronomy and all those things. So this was one of the important discoveries of the recent times in context with astrophysics, and this led to something many different ways, many different theories, and more observations and detectors put into the space, and all those things happened. So what can we learn about it? So this, even before it was detected, there was a simulations done by Takami et al. We showed that how the amplitude and frequency evolves. So here two neutron star merges, and initially there we have something known as the chirp signal, and then once they comes first, there is a first contact, there is a transient part. This transient part differs from groups to groups of simulations, because here most of the high explosive things happen. They first come in contact, there is a huge burst and things. So this part is a bit it depends on the simulation to simulation, with groups to groups, and what is the resolution we are taking into account. This part depends. So but now people have tried to make this transient much more smaller. So this part is the post merger part, which comes just this is the part where we have this part, and then ultimately it forms a black hole during a rundown. So this is the total evolution of a star after it has this binary neutron star merger.
So this transient part is coming at the contact, or
first contact, just when there is the first contact.
And after that, the post merger part, by that you mean where it starts, like in physical?
Yeah, this depends. There is nothing. It's just like in your resolutions, what is the confidence in your resolutions? Okay, this is numerical, right? So in numerical, when there is a huge amount of thing is happening, you are not able to resolve that part. So this transient is that part which we cannot resolve. If you have a huge computing facility, your transient will be very small. Okay, so this is not a part of numerics. It's a part of numerics, but it depends on the resolution that we use. Okay, initially the resolutions they used were quite broad, because quite coarse. Therefore, they have a very broad transient. But now this transient has shrunk very small. Okay, so what happens is given by this cartoon is that two neutron stars, they are merging, inspiraling each other. So we are getting this chirp signal. Once they first come into the first contact, initially there is this transient part, and then it can immediately have a prompt collapse to a black hole, or it can form a hypermassive neutron star, which is this part D. This star is supported by differential rotation and rotation, very high differential rotation and rotation in the star. However, as the rotation and differential rotation ceases or goes down, it can again collapse to a black hole. However, if the star is not very massive, it can form a supermassive neutron star, which can stay. This hypermassive neutron star stays between milliseconds, some tens of milliseconds, but this supermassive neutron star can stay as long as few seconds. However, it can also, after the rotation slows down, it can again collapse to a black hole, or it can form a stable neutron star that we see. So there are the different mechanism or different output that a binary neutron star can have. So how do we study them? So let us just go and have a study. So to study this binary merger, what we need is to solve differential equations, and differential equations which are in 4 dimensions. That means 3 plus 1. What we know from our knowledge of differential equation is that differential equation, we know that wave equation and all those things, we can solve it if I can differentiate, if I can separate out the space part and the time part, right? Wave equation, you know, d square by dx square, we can solve them. D square by dt square, on the other hand, we can solve them. So we want to make them. So in numerical relativity, what we try to do is, so from the Einstein equation, we want to separate out the spatial and the temporal part, so that we can have a, we can solve something as an initial condition here at t equal to 0, let us say, and then we can evolve as a function of t. So that is what differential equation do, and that is what numerical relativity does. It foliates, exfoliates space time. So it has, this is known as 3+1 formalism, that it foliates 4-dimensional space and time into 3-dimensional space and 3-dimensional hyperspace and 1-dimensional time. How does it do? It does with this. We can separate it out by defining a normal vector, which is taking from one hypersurface to the another hypersurface, and we have a spatial metric which is gamma AB, and these are the shift vectors which is defined only on this hypersurfaces, which takes this point to this point, and we have a last function which takes this point to the other hypersurface. So this is how we exfoliate. Then what we do is, we also defined, because this is a differential equation, gamma AB is like a position. Then for, you know, for differential equation, we also have to have a velocity. Second order differential equation, we also need velocity. So this extrinsic curvature is that the Lie derivative of the gamma AB, the spatial metric. So this serves as the velocity. So once we define this two, then we can solve this Einstein equation separately, and we define and we get something which is known as the constant equation, which is the one equation we get from the Hamiltonian constant, and another is the momentum constant. These are the constant equation. These are constant, means this we can solve it as an initial condition in a hypersurface, and these are the source terms which helps in solving this, which is this TAB, right? We can assume it ideal fluid, we can have it to have a viscosity and all those things, but depending on what we choose, we can define the source terms. Next, what we do is, once we have gotten a initial condition in a hypersurface or in a t equal to 0 hypersurface. Now what we got is, we need another two equations which will be my evolution equation, which will evolve my not only my spatial metric and also the curvature, extrinsic curvature. So once we have this evolution equation and the constant equation, we have everything what we need. We have the initial condition and the evolution equation. Also, along with this, we have this GRHD equations, which is the equation that we need to solve when we are solving hydrodynamics. So this is the space-time metric evolution, and this is the hydrodynamic equations, and we need to solve them to solve for binary neutron star merger. So what we do is, and again I have told you, we need an equation of state to solve them. So here what we have done is, and our ultimate goal is to differentiate the equation of state. So here we do a thing is that we construct equation of state. One is hadronic equation of state, which is the blue line, and then we have three different hybrid equation of state. Is that what we mean by hybrid equation of state? Is that from certain density, once it crosses certain density, the quarks begins to appear. Okay, and where the quark will begin to appear, it will depend on how soft or how stiff my equation of state is. So this is the appearance of the quark. You can see that hybrid A is the equation of state where the quark appears at very low density, and hybrid B, it appears at a fairly higher density than the hybrid A, and for hybrid C, it appears at considerably higher densities. So depending on the onset of densities, we have differentiated this equation of state between quarks, not only between quarks but also quarks and hadrons. So these are the 3-4 equation of state that we'll be examining, and how the equation of state, how the binary signature, gravitational wave signature depends on this equation of state. We will be seeing that. So that the evolution equation and the initial conditions are solved using the two codes. One is the Lorentz code, which is the binary neutron star code, which solves the constant equation on a hypersurface. So this is the initial constant equation solution from the Lorentz setup. We have got this initial conditions. These are the two star, and you can see there are bunch because there is some tidal forces between them. And then once we have got this initial setup, we use the Einstein toolkit to solve for this evolution of this star and also for gravitational wave extraction. Okay, so let us now see what happens is there is a video, hopefully it will work. Yeah. So this is how once the neutron star starts, there is a first point of contact, and then you can see this was the first point of contact where the density rises, central density, maximum central density, and it rises, and we have this type of feature, and then ultimately it collapses to a black hole, so it density goes to infinity. Okay, and this is the density, and this is the log of density. To try, this log of density is plotted to see whether there is any mass loss from this binary neutron star merger or not. So this is the simulations that we have. Okay, so this is what happens in a general neutron star merger. Let us see what happens in our case. So we have said that we want to differentiate the equation of state. You can see that from starting from here to here, there is no difference in the central densities, right? But as I cross this point, the central density crosses this point, of the post merger star. What happens is, for this hybrid A, this is a soft equation of state. This equation of state goes to a much higher densities. Okay, the post merger star has gone on to the much higher densities. However, if this was the first initial point, which was much softer, and also the onset of the quark was for this hybrid A was earlier, therefore it has gone to much higher densities. However, as the equation of state becomes stiffer, this density rises for the post merger star is also not very high. What happens is that this is for the 1.2 solar masses, and we have observed this till 35 milliseconds because of computational resource. If I merge a more massive stars, what we'll see that this softer equation of state will go on to form a black hole much earlier than the stiffer equation of state. And you can see that the most stiffer equation of state was the hadronic, which has still not formed a black hole in this case. But ultimately, if I merge very massive stars, everything will ultimately collapse to a black hole. Okay, so this is so the hypermassive hybrid stars are going to form a black hole for this case here much earlier than the hypermassive neutron stars. Okay, so how this will give me any signature of in the gravitational wave? You can see that there is a signature in the gravitational wave depending on what is our equation of state. Is that, see here from this point, our equation of state for the hybrid A and that of the others deviates. So what happens is there is a difference in the phases of this signal, and if we can measure the measure the frequency and the amplitude of the signal, we can calculate this phase difference, and there will be a phase difference between these signals of a hadronic neutron star and a hybrid neutron star. However, if our star has the equation, the hybrid equation of state is much stiffer, the phase difference is much lower, and it is much lower for much higher stiffer hybrid stars. So there is a difference in the observation, but this difference is very non-trivial, is in the sense that we have to not only measure the post merger signal of a neutron star, we have to compare it with another star which we don't have. So that is this phase difference, which were also done. It was done by us, but it was previously also done by many other groups, was not very convincing in the sense that we cannot differentiate equation of state based on this. So what we thought was to try something else. What we did was have an unequal mass binary. So these are the hadronic neutron stars. So two neutron stars, which are for this hadronicity are hadronic matter. But let us say that for a hybrid star, this is a hadronic star which is 1.2 solar masses. There is no quark core. However, 1.6 solar mass for this hybrid A equation of state will have a quark core. Okay, because this mass is larger, so therefore the internal part which can have a, because the central density high, so initially before even collapsing means merging, they have a quark core, and which can happen for hybrid B also and hybrid C, which is not visible but very small. Okay, now if I merge these two type of unequal mass binaries, what will happen? So you can see that the density, the maximum density will rise again. It will rise maximum for the for the most softer equation of state, and it will not rise that much for the most stiffer equation of state. However, the interesting thing comes here. Okay, this is another thing. Is a merger. This is for the hadronic equation of state. You see that there is no quark formation. This is for hybrid B. There is the quark formation here, and it has gone bigger. Here there was not quark formation in the beginning, but as the central density rises, there is a quark formation, and this is the temperature. And you can see that. So this forms a black hole. So temperature here suddenly collapses. The temperature, you can note that the temperature is not maximum at the core, but at this boundary. This is because of the fact that the temperature we are using here is mostly comes from the shock capturing. So where the velocities are higher, the temperature is much higher. Okay, not at the core but at the boundaries. So this is what happens if different type of neutron star merges. There can be difference in the quark signal, and they can also collapse to a black hole. However, the interesting thing is how can we get it in the gravitational signature. The interesting thing that comes is here. This is the part. For a equal mass binaries where there was no quark formation, there was no such signal. But once we have an unequal mass binary and one star has a quark and one star doesn't have a quark, so once it touches just after the first contact, there is initial rise in the quark fraction, and so therefore initial rise in the difference in the phases, which can be captured, because this is a very interesting part, which is not a very slow rise. This is a prompt type of a prompt signal in the phase, and which happens is a feature of every. This is very small because this is very close to that hadronic star. But if my equation of state is much different, then there is this initial signature of this phase difference which can be captured, and this is the thing that can be really probed, because that cannot come from any other structure. Okay, so this is also is seen from this frequency. If I plot this peak frequencies, you can see that the peak frequencies are different, which is also a trivial equation. And if I plot the power spectrum, the power spectral density, we'll see that for the equation of state, which is very different, have different power spectral densities. Okay, so what are the future goals? Is that, see, this post-merger signal that I'm talking about can be probed at least 10 to 15, at least 10 years later, because the post-merger signal can be probed by either Einstein telescope or cosmic explorer. However, there are, along with if two neutron star merges, there are electromagnetic signals, not only gravitational signals but electromagnetic signals can be probed. However, what we have done till now is we have not taken into account any electromagnetic signals, because they are very difficult to control in simulations. Our next task, and we are looking into how to incorporate this GRMHD. We have done till now is GRHD. We have incorporated GRMHD and to have some electromagnetic signals. Electromagnetic signals, people are working 100 years with electromagnetic signals, so they are much precise. And if I have some signals related to this, that can be easily probed. So we are trying to generate a relativistic magnetodynamics course which can have electromagnetic signals that can be probed. Also, we are looking into non-ideal hydrodynamics in the initial to form the initial data, and also different types of equation of state can be probed with this formalism. So before I end, I want to thank my group members. So this work was done mostly by him, me, this person, and another person who has left our group right now. And these are the sites. If you want to look into our work, we can go and visit these sites. And saying that, I should thank you. Thank you for your patience. Hope you liked the talk.